Hello, I'm Poyen.
I'm Peter.
We are master students in Columbia University. Today we are going to introduce our Class D audio amplifier projects in the VLSI Design Lab course. This course is taught by Professor Kinjet in 2014 spring.
What we have accomplished in this project is a Class D audio amplifier integrated circuit, or IC. This is the phototype board of our chip, and the IC sits right here in the middle. It is powered by two AA batteries. The chip receives the audio signal from this stereo jack and amplifies it, and it delivers the necessary current to drive an 8-ohm speaker low, as we have also modeled as a 8-ohm resistor here as well. This board contains all the necessary circuit to power the IC, including the power supply section, the input signal conditioning section, and a triangular wave generator. This Class D design of our chip has the benefit of a higher power efficiency than traditional linear audio amplifier, and it is able to deliver more power drawn from the battery into the speaker low. Next, we'll give you a demo of what our chip does and how it performs. Then we'll describe the theory of operation as well as a block diagram of what our chip contains. For more technical information, please make sure you visit our website listed in the description as well.
As you can see from the screen, this is our 1 kHz input signal, and this is the negative channel output. This is the positive channel output, and by minus the 2 channel, we have the differential output signal here. And as you can see from the screen, we have a gain about 5.
So enough of the graph and oscilloscope. Now we will turn to an actual tone going through a speaker, and it's only being powered by the battery. So it will get a little loud as we first install the battery as it settles into steady state. As you can hear, this is a 1 kHz tone playing through the speaker. This is the final and most important demo of our chip, because our chip right here is designed to amplify audio signal and play them through a speaker. So what we will demonstrate is that using a phone through an audio cable going into our board, we'll have a potentiometer here to adjust the volume. It will play the music through a speaker, all while being powered through two AA batteries. So now let's put in the battery and see what happens. No music because we haven't started playing, and the volume is at the minimum. So let's increase the volume right now. As you have heard, the music is pretty loud through the speaker. In fact, it could fill the whole room. So this demonstrated the success of our chip design as well as our board, that we are successfully able to play the music through any source going into the stereo cable into the speaker. And with just two AA battery powering them, we have measured the current draw from this board, and is much lower compared to your traditional linear amplifier. Now we're done with the demo. Let's take a look at what our chip is and how it does what it does. This is a block diagram of what a general Class D audio amplifier looks like. The input audio signal is being pulse-width modulated when it is compared with a high-frequency triangular wave. The output waveform is a square wave, which the duty cycle is proportional to the input signal amplitude. Next, the PWM wave is passed through a pair of output devices that supplies the current to drive the 8-ohm speaker low. The reason for the high efficiency of the Class D design is because the output devices are either in the on or off state, being driven by a square wave, compared to the linear audio amplifier, where the output devices are either in the active or saturation region, where they constantly draw currents. The Class D design can theoretically achieve 100% power efficiency. Of course now, the output square wave can't be used to drive speaker. So we have a low-pass filter to filter out the high frequency component, and the time average of the square wave is recovered as audio signal driving the speaker.
As you can see from the screen here, this is the detailed schematic of our chips, and we have added a single N2 differential converter here to increase the magnitude of the output signal, and here is the PWM generator. It generates square waves whose duty cycle is proportional to the magnitude of the input signal, and here we have a dead time control to prevent the cross bar current, and after the signal pass through the output stage and output low pass filter, we can recover the low frequency component of the signal, and the signal will be then fed into the speaker. And as you can see, we also have a feedback loop to improve the power supply noise rejection.
Overall, we think our chip design as well as our board design is a success. So in conclusion, we want to thank Professor Peter Kingett for his instruction, as well as the TAs, Chingri and Touche for their assistance along the way. Also, we want to thank Moses for the chip fabrication that they provide us so that we can have an actual chip for us to test. Thank you for watching this video. Hope to see you soon.